Hi guys, today we will walk through another past paper from Unit 6, which is Practical Skills in Physics. And this paper is from October of 2024, so it's quite recent. And I have many others in my collection, but let's start with this one and see how it goes. So, question 1. A student investigated how the current in a diode varied with the temperature of the diode. And they show you a scheme here about what's going on. There's a beaker with water in it, a hot plate, a thermometer, and a diode in there. So, question A. The student varied the temperature of the diode from room temperature to 100 degrees Celsius using the apparatus shown. Identify one health and safety issue and how it should be dealt with. Okay, so this is a 2-mark question, which should take you 2 minutes to solve. So it's quite one of the easy ones. So one problem with this apparatus is that you have a hot beaker, right? Which means that you need to use gloves for safety in case you touch it, in case you want to pick it up, whatever, something like that. And the other problem is that you have wires running through water. So these wires should be insulated. So you might have a short circuit situation due to wires being exposed to water. So you need to use insulated wires, right? So this is how I would answer this question. Okay. Now, part B. The student connected the diode in the circuit shown. So there are two. There is one resistor, and a variable resistor. This is the diode, an ammeter, and a power supply, and a voltmeter, and an ammeter. Sorry. He used the ammeter to measure the current as he varied the temperature of the diode. Explain why the student was correct to include a variable resistor in the circuit. So the resistance, the way to answer this is that the resistance of the diode might change with temperature. Thus, it's a good idea to use a variable resistor to ensure that the potential across the diode is constant. All right. And now we have question C. The student predicted that the variation of current with temperature would be linear from 0 to 100 degrees Celsius. He recorded the following data to plot a graph of current versus temperature. And you're given some values there. Explain whether the unit for current in the table is correct for this data. You should include a suitable calculation. So, what kind of calculation can we do? So we see the circuit here. So we have this resistor and this resistor connected in series pretty much, right? So from the circuit, the total resistance is 100 plus 1000, which gives me 1100 ohms, right? So the resistance is equal to V over I from Ohm's law. So I is V over R, and the voltage in this circuit is 6 volts. I forgot to mention that we are trying to calculate what kind of current there is in this circuit and see and check whether these values make sense. So the current will be 6 volts over 1100, 6 volts over 1100 ohms. which gives us 5.5 milliamps. If R of the variable resistor is 0, then the current is simply 6 over 100 from this resistance over there, okay, which gives me 60 milliamps. So the scale is not suitable pretty much, okay? So I'm gonna write it here. Scale not suitable as I ranges from 5.5 to 60 milliamps, okay? So a current of 4 amps, it's a really large current. I mean, it should get you suspicious there, okay? Right. Question part 2. Give 2 reasons why this data cannot be used to test the student's prediction. Okay, so this is a simple answer. It's a 2-mark question, so it should take you about 2 minutes, or you should raise 2 points or 2 issues about this. So as the question asks pretty much. So 2 reasons. The first one is that we only have 3 data points, and they also do not cover the range from 0 to 100 degrees Celsius, okay? Because we start at 29.5 and end at 50. So we need more data, especially around the 0 degrees Celsius and the 100 degrees Celsius. So not enough data. You can write only 3 data points. And the second one is that they don't cover the range from 0 Celsius to 100 Celsius because they are concentrated between 29.5 and 50 degrees Celsius. So that's not a good range, okay? Okay, moving on to question number 2, which says that the student investigated the free oscillations of a mass spring system using the apparatus shown. So we see that there are 2 springs connected to each other, okay? The student displaced the mass downwards and allowed the mass to oscillate. She used a stopwatch to determine the time taken for the mass to complete 5 oscillations. The student recorded the following measurements for 5 periods. Determine the mean value of the period t. So the first step is to take the average of these 4 values, okay? So let's do that. So 7.69 plus 7.58 plus 7.43 plus 7.51 over 4 yields 7.55 seconds. And this is the time for 5 oscillations. So for 1 oscillation, we have to divide by 5. So 7.55 over 5 gives 1.51 seconds, which we quote in the box there. So let's move to question 2. Determine the percentage uncertainty in the mean value of t. Okay, so first you have to find the absolute uncertainty, and when we are dealing with a series of measurements, that's the half range of the values taken. So the half range is equal to the largest measured time, which is 7.69 minus 7.43 over 2 gives us 0.13 seconds, and therefore the percentage uncertainty in the 5t is 0.13 over the measurement, which is the average value 1.51 times 100, which gives us 8.6%. And then the percentage uncertainty in 1 period is 1/5 of that, right? Because we have taken 4 measurements. So because that's the time for 5 periods. I'm sorry, I got myself confused. So over 5 gives us 1.7%. And recently I have prepared a video discussing uncertainties, which I recommend you watch because I discuss all these things. Okay, part 3. The student measured the time for multiple oscillations and calculated the mean. Describe 3 other techniques she should use to obtain an accurate value for t. Okay, so the first thing she should make sure is to use a small amplitude. Okay, to avoid friction and stuff like that. You can use a tape. She can use a tape at the center of the oscillation. She has to wait for the oscillation to settle before turning on the stopwatch, for the oscillation to settle. And she can also use a camera, okay? Camera usage, which is gonna make her life easier, okay? Now, part B, the student modified the apparatus to investigate damped oscillations of the mass spring system. She placed a circular piece of card, shown here, okay, between the masses to act as a damper as shown. The amplitude A of the damped oscillations varies with the number n of oscillations as this exponential given over there, where A naught is the initial amplitude and lambda is a constant. Devise a method to determine the time taken for A to decrease to half its initial value. Your method should include the use of a suitable graph. Okay, so let's start by investigating this exponential law. Okay, so since this is an exponential law, we can take the log of both sides to find this relationship, which is linear. Okay, so we can plot that. So let's set that aside and say a few things about what we can do, what she can do, the student. She can use a vertical ruler and center the oscillation with a tape. She can start with a large amplitude and count oscillations while measuring A after each oscillation. I hope this makes sense. So you start with a large amplitude and then you start counting. After 1 oscillation, what's the amplitude? After 2 oscillations, what's the amplitude? After 3 oscillations, what's the amplitude? So you have to continuously measure the new amplitude that results from the damping, okay? Then take at least 5 or more, so let's say, or maybe 10 measurements, so you can make a nice plot, okay? Plot the log of the amplitude versus the number of oscillations. Calculate lambda from gradient, right? And then you can plug that in to find n. So how are you going to do that? So the half amplitude satisfies this relationship, right? If the amplitude reduces, we are interested in finding n, okay? So when the amplitude reduces to half, this relationship applies. We know lambda from the graph, so we can delete that. and solve for n, which gives us ln of 2 over lambda. Okay, so this is the number of oscillations. So this quantity over here, ln of 2 over lambda, is the number of oscillations needed before the amplitude reduces to a naught over 2. Okay, and the time needed for that to happen will be n, the number of oscillations, times the period. Okay, and this is the answer. We can move on to the next question, which gives us the luminosity L of a main sequence star, and it is stated that this varies with the mass m of the star. The relationship between luminosity and mass is given by this relationship, where L, that's L sun. So the sun in astronomy is denoted with this symbol over there. And I think the Earth, you can check, I think this is the Earth, okay? Which is also the symbol for a female, I think, but you can check for yourselves. So anyway, that's the relationship. Explain how a graph of log of L against log of m over m of the sun can be used to determine the value of R. Okay, so this is similar to the previous problem. So we can take the log of both sides. So log of L will be log of L of the sun plus R, and then the log of m over m naught. Okay, so this is of the form y equals mx plus c. So this is a constant plus mx, where m, the gradient, is equal to r. So that's the gradient. Okay, now the data for 6 main sequence stars is given in the table shown here. Plot a graph of log of L against log of m over m naught on the grid in the opposite page, on the grid opposite. Okay, so this grid over here. Use the additional columns for your process data. Do not convert the values of L from 10 to the 35 watts to watts. So it is advised that we keep it to 10 to the 35. Okay, so I will speed this part of the video up, or maybe edit it out. But anyway, in the next moment, I guess you're gonna see the data and the plot. So let's do that. So this is what the plot will look like. Be careful with distances you put, and you can use these squares to find a suitable range for your data, etc. But anyway, let's move on. It's really difficult to talk about the graph in these videos. So let's move to determining the value of R from the graph. So the way to do that is, let me find the R. You can take the extreme values from your data pretty much, okay? 4.49 minus 0.39, for example. So 4.49 minus 0.39, because these are plots are data from your graph, over 0.81 plus 0.33 gives us 3.6. Okay, so that's R. Determine the value of the luminosity of the sun from the graph. So log of L of the sun from the graph is about 1.5, which yields that the luminosity of the sun is 31.62 times 10 to the 35 watts, which you can write as 3.2 times 10 to the 36 watts. And then it says a particular main sequence star has a mass of 33 times the mass of the sun. Determine the luminosity L of this star. So we can just do L is the luminosity of the sun times the mass of the star over the mass of the sun to the sixth. Okay. So to the 3.6, I'm sorry, 3.6, which is R. And if we continue this, we will find 9.37 times 10 to the 41 watts. Okay, that's it. And now the last question. So a student made measurements of a wooden meter rule. The width of the meter rule was A, and the thickness of the meter rule was B as shown. The student used digital calipers to measure A. Explain one technique she should use to measure A. So you have to repeat at different positions and take the mean to minimize random error. This is the answer, because if you want to measure A, maybe the width here is different than the width here, and maybe the width here is different than the width here. So it's good to take multiple measurements and average. So repeat measurements at different positions and take average to minimize the random error. Okay. B, the student clamped the meter rule to a bench. She attached a mass M at the distance D from the clamp as shown below. The student displaced the mass vertically and allowed it to oscillate. She measures the time taken for 20 oscillations, 20t, where t is the time for one oscillation. She repeated these measurements several times. The meter rule is made from wood. The Young modulus E of the wood is given by the formula 16 pi squared times the mass times d to the third, where d is this quantity over here, over A times B cubed times the period squared. Okay, so that's quite of a formidable expression, but let's move on. The student increased D and measured 20t several times. Again, explain how increasing D affects the percentage uncertainty in the measurement of 20t. So recall that the percentage uncertainty is equal to the absolute uncertainty over the measurement. Okay. So in our case, the percentage uncertainty in D is the absolute uncertainty in D over D. So increasing D reduces the percentage uncertainty. Okay, simple as that. Part 2, the student recorded the following data. Everything's given there. Show that E is about 14 gigapascals. Okay, so E is given by 16 pi squared md cubed over a b cubed t squared. And if you plug in the values given, notice that be careful for the quantities given in millimeters, convert them to meters by multiplying to the -3, okay, because they're given in millimeters. So, and this will be 6.17 times 10 to the -3 meters. Okay, everything else, and the mass should become 0.4 kilograms. And if you plug everything in, you find 1.43 times 10 to the 10 gigapascals, very close to what we are asked. Okay, show that the percentage uncertainty in E is about 5%. Now, how do we find that? So the percentage uncertainty in E is equal to, okay, this is a little bit involved. you have to watch my video on how to work with uncertainties, but here we are dividing physical quantities, and when we are dividing physical quantities or multiplying physical quantities, we just sum their percentage uncertainties, okay? And when we want to find the error in some measurement, in some physical measurement that is raised to a power, we multiply the percentage uncertainty with the power, okay? So here we pretty much have to sum the percentage uncertainties of all these quantities. So 3 times the percentage uncertainty in D, because D is raised to the 3 power, plus the percentage uncertainty in A, okay, plus 3 times the percentage uncertainty in B, plus 2 times the percentage uncertainty in T. And then the mass that appears in the numerator does not have an error because it's coded without an error up here, okay? And the constants do not matter in percentage uncertainty. So if you add this up, so to find the percentage uncertainty in D, you just divide 0.001 over 0.8 and then multiply by 100. And if you do that, you find 4.77%, which is close to 5%. Okay. And the last question is the value of E for Beechwood is 11.9 gigapascals. Deduce whether the meter rule could be made from Beechwood. So E is 11 for this material is 11.9 gigapascals. We found 14.32 gigapascals. And then if we multiply with the percentage uncertainty, we find the absolute uncertainty, which is 0.68 gigapascals. The absolute uncertainty tells us that the real value of the measured quantity is 14.32 plus or minus 0.68 gigapascals. So if we subtract 0.68 from our measured value, we find 13.64 gigapascals. So that's the lowest range, okay, which is higher than the quoted value of 11.9 gigapascals. So it's not that type of wood, okay? And this is a quick walkthrough of the Unit 6 paper from October 2024. I hope these videos are useful. Let me know what you think about them in the comments, and I will keep them coming. And please like and subscribe, tell your friends, and so on. Thank you, guys.